Starting a recording, and you will probably see a recording starting on your behalf as well?
Yeah.
Okay. So, thank you for doing a part two, Josh.
No,
Or
very,
Josh.
very happy
What
to
do
be.
you prefer, Joshua or Josh?
It is
that...
fine. I have no
Okay.
real preference.
Cool. Okay, so I've been reading up on the protocol and been a little bit in your Discord channel. That's a very inspiring environment with a lot of knowledgeable people. And the protocol is per now 54 pages with a lot of information. And there's a lot of things there that strikes me. But one special thing that I read this morning on the way to this meeting and work was this catch-22 situation, where people who are in a MS, CFS or similar situations, they do not want to exercise because the immune system boosts up and try to battle the pathogen and viruses, and then it makes them feel extremely bad.
That's right, the oxidative stress issue.
Exactly, and then they do not want to exercise. But that keeps them in this catch-22 situation. So
that's right.
It seems like you have to go through like you said in the paper, no pain, no gain, but you have to pace yourself. And of course, all these supplements and things you take are to make sure this transition is
smoother.
possible.
So it's really important. So this is the thing, like if you without all the rest of the supplements and the things that we're doing in the protocol, if you were to jump in and do any kind of exercise, you're going to end up drowning in oxidative stress. And that potentially can drive the situation backwards. It's key to understand that, somebody who does have CFS, if they take some bad advice somewhere and just exercise because they get told that that's what they should do, it's going to go very, very badly. If you are supporting the oxidative stress, if you're supporting it in a way, I mean, ultimately what has to happen is that the minerals that are required for the enzymes to metabolize those reactive oxygen species and reactive nitrogen species, if the minerals are put back in, then the exercise doesn't become a problem. Like the issues you have with the post-exertional malaise gone. It's actually really simple to solve. However, in the early stages, we go to a lot of extra effort to try to boost up the body's ability to metabolize those reactive oxygen species using, well, cannon fodder, for want of a better word, things like ascorbic acid and various other, diet-based antioxidants. But once the minerals come up, then the body's able to metabolize those in its normal way, and so therefore the immune response becomes no longer inappropriate.
So there is a big discussion where I live in Norway that people who are suffering from these conditions are asked to be part of the kind of think positive processes and go into exercise. So these people are partly right that this is good, but they don't understand the danger of just pushing these people over the edge.
It can go horribly, horribly wrong. And look, there's been quite a history with, graded exercise therapy, or GET. And it's usually, the proponents of GET and CBT. And I have to really, really clarify that that's not what I'm saying in the protocol and in the model. It's look, the exercise, the exertion generates the metabolites that are needed for that immune response. Without that exertion, then the immune system is hampered. It's going to be, having difficulties in generating the response to these, these different pathogens. But the problem is that the fact that the immune cascade intentionally generates oxidative stress or reactive oxygen species, then we need to actually fix the other side of the equation. We need to fix the enzymes, or the metalloenzymes, which are needed to metabolize the reactive oxygen species first. So that's like CuZn SOD, so copper zinc superoxide dismutase. You've got Mn SOD, so that's manganese superoxide dismutase. You've got catalase, which is heme, a form of iron. You've got glutathione peroxidase and reductase, and that's a little bit more interesting. So you've got the minerals that are required for the riboflavin metabolism to get to FAD, which also then means the thyroid metabolism to generate T3. So you've got essentially iodine, selenium, you've got calcium, you've got zinc, molybdenum, and heme yet again. And then, yeah, it's really... when you look at the data, you can see the patterns. You can see who's going to be having those difficulties. And you can see straight away, when the minerals come up, for copper and zinc in particular, providing the others aren't so bad, the issues with the post-exertional malaise disappear.
That's really interesting, because what you're referring to now is, of course, testing as a start of the protocol to get an overview of what kind of setbacks you have in different areas of minerals and vitamin and etc. And this is like interesting. Do you? I don't remember I've read it, but do you think that the viruses and pathogens want the body to stay in this catch-22 situation? That's how they survive? Is that some?
Not exactly. I think, look, the interesting thing is, so what happens there is that there are certain cytokines which inhibit these mineral transporters, and it's an intentional. It does actually benefit the host in a short-term situation, like an acute infection response. So when there are elevations of cytokines, so tumor necrosis factor alpha, IL-1 beta, 6, 10, and 22. If they're elevated, they promote or elevate a peptide hormone called hepcidin. And hepcidin is most commonly known for regulating iron homeostasis, but in the literature, when you go digging through it, it's actually responsible for 8 other metals as well. So you've got 9 metals in total, which are then going to be controlled or regulated by the levels of hepcidin. And so what happens is that there are different cells in the body that have 2 different transporters. So certain cells, like the gut, so the enterocytes, they've got divalent metal transporter 1, DMT1. So that's responsible for pulling in the metals, those 9 metals, into the cell. And then there's ferroportin, which you would think only means that it transports iron or ferritin, but no, it's equally responsible for the others. It's the one that transports the metals out of the cell. So when hepcidin is elevated, the enterocytes, they block the absorption of the metals from the gut, and they block the transport of it back into the circulation. Now, in other cells, so the cells in the brain and the cells in the kidneys, sorry, the liver, I think, and the kidneys, they only have ferroportin. So what that means is that they continue to pull the metals into the cell, but they don't release them. So that's the mechanism via which how the metals get sequestered out of the circulation during an inflammatory state. And so the benefit to the host in the short term would be that it then makes those metals not available for any circulating pathogens for replication. So the existing cells, like the immune cells and things, would have the upper hand in that short-term situation. But when it becomes chronic, the host ends up becoming depleted in those minerals. And the worst part about this is the more severe you are, the harder it is to get those minerals back in. So that's the catch.
Can you just explain why it's harder to get those minerals back in?
So the levels of the cytokines are going to be going up and down and up and down all day.
Yeah.
So the more issues you have with that inflammation, the less of an opportunity you may have to absorb dietary minerals. So you get a window of opportunity to absorb the different nutrients that's come out of the food that you've consumed. And if you have a period of inflammation during that absorption window, then you're going to be not getting the metals from that meal. So it's a challenging one. And due to the fact that a lot of the inflammation is actually coming also from toxins that are being produced, or the response to the toxins that are being produced by the microbes along the way in response to the food, it can get quite tricky. So the more severe the dysbiosis, or the more leakier the gut membrane or any of the other mucosal membranes are, the more issues they're going to have. And of course, there's additions there. If you've got intracellular bacteria, spirochetes, Lyme disease, that kind of thing, you've got the same sort of process going on, but different compartment. So yeah, the more the pathogenic burden, the more the inflammation, the less capable the host is of energy metabolism and generating certain types of inflammation, the harder it gets to maintain those minerals. Unless, of course, you sidestep the whole problem and either put the minerals back in via IV or via a different route, example, sublingual, or even rectal administration in some cases.
So
it's
IV would be a good
IV is
idea.
great. Yeah, I've seen a few examples of that now, and you can restore those minerals in a matter of just a couple of weeks.
That's crazy. So
Yeah,
because
whereas
in the protocol we're talking about sublingual with this
troches or the lozenges.
yeah, and this what's this drops of this earth compound that's when the earth degrades, you get this special kind of liquid or something What is
fulvic acid and humic acid.
exactly?
Yeah, no, that's okay. That's later in the protocol. That's actually quite an interesting thing. So that acts like a wrapper for a lot of these, like it's essentially binds a number of these metals and other things and is able to then transport them through cells using a different route.
Okay, so those are not used for remineralization.
Not at that point. We bring that in stage 3. The fulvic acid has other functions. So it's really good for biofilm breaking. So stage 3 in the protocol, jumping ahead, one of the things that we're trying to do there is break down circulating biofilms as well as the ones that are in the mucosal tissues, and at the same time as modulating the immune system to affect a really robust immune response. So once we've built up the capabilities of the body so that it can sustain exercise and it can sustain immune activity, then we want that immune activity to proceed with as much efficiency as possible. And so to do that, we remove the barriers to the immune function. So in other words, we remove the biofilms which are cloaking these pathogens from immune surveillance, and we ramp up the production of NK cells and other cells using some of these immunomodulators and stimulants, like from reishi mushroom and lion's mane mushrooms and beta glucans and things that we're including there.
Okay, so the last question about what I've been looking into: is it possible to say that you have Candida and Epstein-Barr? Is it possible to get rid of Epstein-Barr, or is it about getting the body to control the situation?
Okay, so important to understand. So Epstein-Barr virus in its latent state is not triggering an immune response.
Okay.
So because it's the immune response that's actually generating most of the symptoms that people suffer from, and unfortunately most people think of the symptoms coming from the pathogen rather than the symptoms coming from the response to the pathogen, gets very confusing for them. To put the virus back in its box or back into latency is not challenging.
Okay.
So so the immune system, if it's capable, will attack the lytic cells, but the latent cells are hidden. So if you want the immune system to, stop attacking lytic cells, you just need to not have any lytic cells. And so then you've got to take a step back and say, well, hang on, why are these cells activated or reactivated in the first place? And again, that comes back to problems with the mitochondria and or mitochondrial dysfunction and the hypersensitivity in these enzymes that act as a metabolic sensor called prolyl hydroxylases. So prolyl hydroxylases, they look for hypoxia, they look for oxidative stress, they look for an impaired citric acid cycle by testing for low levels of alpha-ketoglutarate, and they're sensitive to low levels of iron, zinc, and silicon. Silicon is actually really interesting because the silicon, when the body sequesters the iron out of the circulation, the silicon is supposed to still be there to act as a buffer against this particular activity becoming the prolyl hydroxylase activity becoming hypersensitive. So if you have low silica, which unfortunately is also part of the model that comes from something else, this is another issue where the silica appears to be binding to the acetaldehyde in the stomach and then forming an adduct and then being excreted in the urine. Once you get the low silicon, then you have problems with collagen synthesis, or one of the many problems that create collagen synthesis. Or impair collagen synthesis. But yeah, also it means you become hypersensitive in the case of an immune activity, causing then reactivating Epstein-Barr virus or any of the other herpes viruses that use this same mechanism. So the same thing which triggers lactic acid metabolism or anaerobic glycolysis is the same thing which triggers the reactivation of those viruses. And that's a protein called HIF, or hypoxia-inducible factors, which is controlled by the prolyl hydroxylase activity. So if the prolyl hydroxylase activity is inhibited in any way, then that HIF enzyme becomes stabilized or promoted, which then allows for the reactivation of those herpes viruses and HPV and HIV at the same time as the lactic acid metabolism is triggered.
Okay, so all those kind of, you even mentioned HIV virus in some people, did you? Okay, so all those situations with having latent viruses, it should be no problem for the immune system. So we don't really have to think about just finding something that eliminates it entirely from the body.
From a CFS point of view, we're not as worried about the latent infections. They do still have relevance to cancers. They still have relevance to senescence, so aging and things like that.
Yeah.
But relevant to triggering the symptoms that we get in CFS, no.
Okay.
I can't see any mechanism for that.
Is there anything that is included in the protocol that actually there are some research on that it actually could remove the virus from the body. For example, I have read a lot of articles about active hexose correlated combine. What's it called?
So
On the HPV virus. That's
so
alpha
for
glucans.
Yeah, well, there are a few things in there which can. So, for example, if you look into the literature for Epstein-Barr virus,
Yeah.
you've got the black seed oil has a
Mm.
function in being able to remove the masking or the if you like, the blind spot for the immune system for EBV. There are a number of other things. Reishi also potentially has the ability to do that. There is something which I will be looking to include after all of these stages. There's something I'm working on at the moment, which is agnostic to a number of these different infections and cancer cells and senescent cells. What I've actually got is a mechanism, and this isn't in the protocol yet. This is still going through the paces, but it's a mechanism which allows you to select cells using Warburg metabolism for necrosis or apoptosis. So in other words, if you have a latent herpes virus or HIV or HPV, if you have senescent cells, if you have various cancers, then yeah, there is a mechanism by which you can induce the necrosis of that cell by removing the remaining energy pathways which are available to it.
Is this something
if you
that
were
happens
to,
in fasting? Also,
fasting does have a mechanism for that, but this is something different. Look, I'll jump ahead to this. I'll explain it. I'll explain it because, look, it's not, I haven't really written it in too many places. You'll find it in the Discord. But so if you look at Warburg metabolism, so the way that that's actually described is that you have a cell using lactic acid metabolism and glutaminolysis. So that's where essentially you've got anaerobic glycolysis and glutaminolysis. So you have the cell using lactic acid, but you also have glutamine becoming the preferred substrate for the citric acid cycle. So glutamine goes to glutamate, glutamate goes to alpha ketoglutarate, which then enters the citric acid cycle. If you consider for a minute that the reason that that's happening is because glycolysis has been impaired, and maybe fatty acid oxidation has also somehow been impaired, and there are various ways that that happens. It means that there are still these remaining pathways to keep the cell alive. I mean, any cell can use Warburg metabolism when it's sufficiently stressed. When we're looking at things like lactic acid metabolism in exercise, for example, and glutaminolysis in exercise, and also under exertion or mental exertion, even the brain's quite able to use these pathways. The issue with these cells is that they don't actually have the ability to still use normal glycolysis. They don't actually have, fatty acid oxidation working. So if you inhibit the lactic acid metabolism and if you inhibit glutaminolysis systemically, then all of the cells that can still use the standard pathways, they don't really notice that there's a problem. They continue to operate as normal. But the cells that are remaining alive by using lactic acid metabolism and glutamine as a substrate have just lost their fuel sources. And there are only really options there to keep that going. I mean, look, there's still the urea cycle, and you can use benzoate to drain that. But there are only small amounts of substrate available via anaplerosis to keep those alive. So the cells pop.
So it's interesting. That's why, like, people in cancer are hear about they should not eat carbohydrates, and that's what you're talking about, like carb and keto. If you remove those pathways, there's another that you call Warburg. What kind of nutrition are you talking about? Where is the food source?
Well, Warburg still ends up fermenting, so it uses lactic acid, which ultimately still comes from that glucose pathway, the glycolysis pathway. But then there's a bit of a difference there, and it ends up becoming lactic acid, converting into pyruvate back and forth and back and forth. The glutaminolysis, glutamine can pass between cells and tissues quite freely. There's about 81 grams of glutamine in a body in a typical 70-kilo human being, which is enough to sustain cells for quite a long period of time. So it's kind of like in many ways, if everything's going well and there's no energy shortfalls, the body's able to use glycolysis and glutaminolysis at the same time for additional energy. So but in the cases where we've lost the primary energy pathway, so glycolysis and fatty acid oxidation, for example, then yeah, it becomes then it's like a backup substrate or a backup pathway to maintain, the cell's viability.
Yeah, and what kind of food are we talking about? Or what kind of, like, let's say you want to shut down the cancer cell that feed on those traditional pathways
Okay.
and go over
So
to the Warburg.
it's interestingly enough, okay. So what you could expect is that the sensor enzymes, so the prolyl hydroxylases, they're still going to end up failing. So they become inhibited because of the conditions inside the cell. That could be oxidative stress. That could be a number of things that are happening. So then you don't want to target the prolyl hydroxylases directly. You can go one step beyond that and target hypoxia-inducible factors directly. You want to inhibit that protein. So even when the prolyl hydroxylases become inhibited, it doesn't allow the protein to become stabilized, which then prevents the transcription factors from allowing the lactic acid metabolism. And as it turns out, the active form of vitamin A. So vitamin A, just to take a step back, you've got retinol, which then gets metabolized to retinal, that's the aldehyde, and then that gets metabolized into retinoic acid, which is the active metabolite. So it's all trans retinoic acid. Is the active version of vitamin A. And funnily enough, that gets used for acne. So tretinoin is the trade name or the drug, which is all trans retinoic acid. So in some of the studies, they have actually explored this. They've used all trans retinoic acid against various cancer cells, and it has the effect that we're describing. So it actually induces the necrosis. But what they hadn't done in those studies was then say, okay, well, what happens if we then, remove the other pathway as well, the glutaminolysis? How much more effective is this going to be? So as it turns out, inhibiting glutaminolysis is not particularly challenging. There's only, 2 steps to go from glutamine through to alpha-ketoglutarate. And one of those enzymes is called glutamate dehydrogenase. And glutamate dehydrogenase happens to be inhibited by a green tea metabolite called EGCG. So EGCG plus the active form of vitamin A, so tretinoin or all-trans-retinoic acid, systemically, for somebody, and this is really important, for somebody who doesn't have CFS or impaired metabolism or type 2 diabetes or whatever you want to look at as impaired glycolysis, if you were to use that intervention, you would be able to induce selectively necrosis in those cells. But if somebody has CFS metabolism, the body is already using lactic acid metabolism regularly and glutaminolysis regularly. That's how the cells are managing to stay alive while we've got the problems with glycolysis that we see in CFS. So you can't use this particular methodology for somebody that's still dealing with the mitochondrial dysfunction. You have to fix that up before you could use that. This is why I'm saying I'm looking at this to add on later in the protocol after you can quantify. And there are a number of tests that you can use to indicate the fitness of the cells and how much they're using lactic acid metabolism already, and look at the glycolysis efficiency and things like that. So things like the organic acids test, or the LDH, so lactate dehydrogenase isoenzymes test, which then allows you to look at the LDH protein levels in different tissues. So the different isoenzymes allow you to kind of get an idea of, is this liver, is this muscle, is this brain, lungs, like which cells are using lactic acid metabolism.
Would you say that that would be like the intervention that you do intermittently, and a person who are affected with certain cancer, and would they combine vitamin A and the active version of vitamin A and ECGC with some kind of fasting or typical
I wouldn't do it while fasting.
restriction?
In fact, yeah, I would. Okay, and again, this is purely hypothetically, not medical advice.
Exactly. Yes.
Right. If I was to explore this, and I'm known to guinea pig myself on various things, so it could be a discussion we could have at some point. It would be the kind of thing that I would want to be fed. I'd make sure that I have sufficient liver and muscle glycogen. I wouldn't be exercising. I wouldn't be trying to stress, any of the other cells in any way. And I might, for example, I might have, as a 70-kilo person, I might have 600 to 700 milligrams of all-trans retinoic acid at the same time as I had, probably in the same sort of vicinity for EGCG.
And you shouldn't have
And
EGCG with protein together, right? Because that would, I read that if you have EGCG with protein, that could mess up the absorption of EGCG.
Yeah, you would want to have them generally separate to things. I mean, EGCG before meals or after meals works okay.
Yeah,
But I think Yeah, I don't know how overblown that one is. I
Yeah.
think it's probably not a huge issue.
Okay. Then you would.
Yeah, and then I would also throw in some sodium benzoate to drain the urea cycle. So the interesting thing is that the urea cycle can also become another source for the citric acid cycle at fumarate. So if you wanted to create a different pathway to convert the ammonia that would normally go into the urea cycle and go somewhere else, sodium benzoate is one mechanism to create that. It then forms hippurate, but that needs vitamin B5 or coenzyme A, and I think glycine from memory to form hippuric acid or hippurate. So that then keeps the substrate out of the urea cycle, which then means that it's not able to keep the cell alive via that pathway either.
That's crazy.
Hmm.
I think this is really interesting, and I think this was a worthwhile route to discuss also. But going back to CFS, and do you have something to show that you can explain at the same time regarding the protocol and the mechanisms we are talking
Sure.
about regarding CFS?
Yeah. Look,
So
I
because some
think we
people
could
are
go
more
through.
visual, and this is a quite complex subject also, so I think that would be really,
I
really
think it's an
beneficial.
incredibly complex subject. It's
Yes.
funny, it actually once you actually get a number of the concepts, it becomes much easier. It's kind of like if you've got the jigsaw already, three-quarters filled out, then it's easier to kind of put the rest of the pieces in. But it's what I might do is just bring up, I'm not sure if I've got screen sharing functions. I'll bring up
Yeah, I
a
think so.
high level diagram and maybe step through. Let me just see if I can do this. It looks like
Because
I can.
I look so like angry or strict in my face, because that's just me trying to hang on for dear life, because I am a social scientist and this is super complex and super interesting. So any person watching, that's what's going on. I just love it and think it's really interesting to, yeah, I really love it to listen to it, even though it might not look like that on my face. So, okay, what we got here?
Okay, so this is a high level. This is a very simplified overview of the ME/CFS pathophysiology. So it starts off as microbiome dysbiosis, which can be created from a number of different angles, and it can even come from vertical microbiome dysbiosis or diversity loss,
Can
which
you
might
just
come from the mother.
explain the dysbiosis for those people who didn't get that
Yep.
concept?
So dysbiosis is a very broad term, but specific to the model. What we're talking about is very low levels of the Bifidobacterium species in abundance, and also the Lactobacillus species diversity and abundance, relative to an increasing level of acetaldehyde producing species. So that might be Candida, that might be Streptococcus, Staphylococcus, Klebsiella, I think a number of the others there which are able to produce it. And what you then end up with is a net increase of the primary ethanol metabolite, acetaldehyde.
Hmm.
So acetaldehyde, this is why the disease really looks a bit like beriberi, if you've ever come across beriberi. It's almost like because of the oxidative stress, you've got effectively like scurvy, because the effect of having low vitamin C, which is then going to create a number of the issues that you also see in scurvy. And it's like chronic alcoholism
Hmm.
without any of the fun parts. And this is also why you more often than not, you'll find that people with CFS are intolerant to alcohol because they already are processing vast amounts of it.
Jesus. So it's like having a constant hangover. Would that be
Yes,
a?
chronic hangover syndrome might be a
Oh
better
my God. So
with
people
a
can
side of
relate to
scurvy.
it. I think you would get a lot of more empathy if people understand it's like having a constant hangover.
Yeah, well, if you had higher levels of the alcohol, it would be auto brewery syndrome.
Hmm.
But that's not detected. You normally don't see the alcohol levels.
Hmm.
Occasionally, where people have been able to get tests for acetaldehyde, you'll see the elevation of acetaldehyde. And there's a conflict. There's a particular conflict in this model because the enzymes which are processing the acetaldehyde are sensitive to NAD. And the NAD happens to be, and NAD is like a currency. So you've got like the vitamin B3 active metabolite is NAD. or you'll see it written as NAD+. There's the reduced form, which has got an H on the end, so NADH. That NAD is required by an enzyme called aldehyde dehydrogenase. What I might do is just jump away from the simplified diagram, and I'll just go back to some of the where is the
zoom? Maybe down to the right. There's a 17% zoom right there. There's a
there we go. There you go. No, I had the yeah, I had the right. So if we were to look at ethanol metabolism, and you'll notice there's a number of species mentioned here in orange. Okay, so normally ethanol can be metabolized by 3 different enzymes into acetaldehyde. And you'll see that one of the enzymes is alcohol dehydrogenase, which requires NAD. And then the NAD pool is reduced to become NADH. So NADH becomes elevated, NAD becomes low. The 2 other enzymes that can also metabolize ethanol into acetaldehyde would be catalase, which needs heme. That uses NADPH as a cofactor, which then returns NADP. Likewise, CYP2E1 is another one, very, very similar. So it's using NADPH as the cofactor. Regardless, we end up with acetaldehyde, and there are limited options to convert the acetaldehyde into something that's not toxic. So ALDH2, which is the mitochondrial aldehyde dehydrogenase, it is the most productive enzyme, or it has the highest affinity for the acetaldehyde, as I recall. But some of the other ALDH, so the other ones which are responsible for the dopamine, norepinephrine, and epinephrine degradation. So ALDH1 is also sensitive to acetaldehyde. But you'll notice again, so we have NAD as a cofactor, and we have certain minerals, so molybdenum, zinc, and magnesium, which are needed for this activity. So if we have various deficiencies for those minerals, we're going to have less activity. If we have problems with the levels of NAD, then we're going to have less activity. And conversely, the other way around, if we have a large acetaldehyde burden, then it's going to have an influence on the levels of the NAD and the NADH pools. So by virtue of having to process all of this acetaldehyde, the levels of NAD are going to be low, and then the levels of NADH are going to be elevated. So that's going to have an impact on a number of different parts of the metabolism. Now, what
does that
gets really
also to have that kind of environment? Would that also benefit one type of flora in your gut or system, like one type
the
of
NAD? Well,
no, like
NAD is
to have chronic acetaldehyde, would that benefit one type of
probiotic? It'll absolutely influence the microbiome makeup and the distribution. So it's one of the reasons that people who drink a lot of alcohol might also have other problems with candida and things like that as well.
Okay.
Now, one of the other things that's really interesting is the immune response, and I might just jump to one of the other figures for a moment. This is a little bit complicated. There is actually on the website, we've got an interactive diagram explorer, because normally when you're looking at this, you can just see there's just lines everywhere. It becomes very hard to navigate. But on the website, you can click on these boxes and they light up the paths, and you can just work your way through the logic of the model. So one of the things is, just sticking to this area for a moment, so interferon gamma, which is the one which produces the reactive oxygen species to oxidize the pathogens. So it's promoted by temperature and it's promoted by exertion. And what happens then is that it then increases certain enzymes that produce these reactive oxygen species. So you have xanthine oxidase, which is known to take, from memory, it's purines, and then produce reactive oxygen species and uric acid. So when people talk about gout, for example, they're really talking about excess activity in xanthine oxidase. In other words, a localized infection, which is using interferon gamma. The other enzymes, we've got NADPH oxidase, which is a very interesting one. And then we've got nitric oxide synthase. And nitric oxide synthase is a very complex enzyme because it becomes sensitive, and I'll show you how that reaction looks in a minute, but it's sensitive to things like BH4, so other oxidative stress levels. It needs zinc, it needs calcium, it also has a requirement for the active ribophosphate. It's a very complicated enzyme. But ultimately, what all of these things do is that they create this reactive oxygen species to then oxidize the pathogens, and potentially under poor circumstances where the minerals are low, that might then cause damage to the epithelium or the mucosal tissue, so the barrier function, which can then also create a ongoing cycle, because if the foreign cells or proteins are getting through the barrier, then the antigens are going to be triggering an immune response. So that can turn it into this ongoing cycle as well. But what's really interesting is that the interferon gamma at levels, when they're elevated via a mechanism, at least in one study, it showed that NADPH oxidase being promoted then caused the inhibition of mitochondrial complex 1. And now, for people who don't know what mitochondrial complex 1 is, or NADH dehydrogenase, what that does is, in the citric acid cycle, just jumping back to this, in the citric acid cycle, you have a number of reactions which generate NADH. So it takes NAD, goes through a particular reaction, it then creates NADH, and that NADH, or that pool of NADH, then goes on to the electron transport chain. And it does that via an enzyme that's sitting on the inside of the mitochondrial matrix, which I haven't got a diagram for in front of me, called complex 1, or NADH dehydrogenase. And so what that does is it takes the H off the end, the hydrogen, takes these 2 electrons, pipes them down the electron transport chain, go via the multiple steps to eventually power the pump that's called ATP synthase. So that's where we get the ATP from. However, there are a number of other enzymes that do that. I mean, there's complex 2, which was this little one over here, so succinate dehydrogenase. And there are a number of other mitochondrial, enzymes on the inner mitochondrial matrix, which are also able to act as an electron donor. I'll come back to that in a minute. But for now, that NADH, so all of that NADH, which is being generated by the citric acid cycle, instead of it going onto the electron transport chain, instead that pool of NADH is going somewhere else. In fact, it goes everywhere else. But in particular, what it's able to do is act as a promoter of another enzyme here called NADP transhydrogenase. So what happens here is that NAD goes through NAD kinase, it then is able to produce NADP, and then that pool of NADH then drives the conversion of NADP into NADPH, returning the NAD. So even though mitochondrial complex 1 is no longer transferring those electrons, instead of that, we're then ending up with this increasing pool of NADPH. So that NADPH is able to be used by the immune response. So again, here, when we're talking about NADPH oxidase, but in particular, that NADPH is used by the hormone biosynthesis pathways. It's used by the cholesterol biosynthesis pathways. If you look down these pathways, you'll see there's things like the adrenodoxin reduced, which is used in the first couple of steps here, from cholesterol through to pregnenolone. You'll see that there's NADPH and FAD. So every time you see adrenodoxin reduced, each one of those is using NADPH. Likewise, if you're looking further along the pathway here, so progesterone through to eventually aldosterone, you'll see NADPH, NADPH, NADPH. So it is used all over the place in biosynthesis pathways. There's some regulation here via cortisol, and I'll come back to that. But if you were to look at other places in the metabolism that use NADPH, again, methylation. So when we're converting folate through to THF, tetrahydrofolate, that's then requiring DHFR, which is then requiring NADPH. Similar, you'll also see that MTHFR, which is one that everyone loves to talk about, that also uses NADPH as the cofactor. So what that means is that MTHFR here is actually controlled by the levels of NADPH and NADP. So if NADPH is elevated, then the reaction here is going from 510 MTHF to 5 MTHF. So if we have a very high level of NADPH, the activity is basically biased towards converting 510 MTHF into 5 MTHF. Similarly, if we were to look at other parts of the metabolism, you'll see that NADPH is also used for protein synthesis, for collagen synthesis, and for repair. So we can take glutamate over here on the right. That'll be converted into P5C, pyrroline 5 carboxylase, which is then goes through P5C reductase, which also requires NADPH. Likewise, if we're looking at the activity from glutamate just through to pyrroline 5 carboxylase, you'll see NADPH, NADPH. And you'll see the same thing here for nitric oxide synthase, which is the other interferon gamma sensitive enzymatic reaction to produce the reactive oxygen species to oxidize pathogens. There are a number of other places that you'll see it too, but largely synthesis tasks are going to be promoted by the elevation of NADPH. Cholesterol biosynthesis, as I was saying, was the other one. So look, what that basically suggests is that interferon gamma is responsible for orchestrating hormone biosynthesis. And so it's really interesting that interferon gamma, as well as being responsible for the immune activity that we're talking about here with this reactive oxygen species generation, it's also used by the tissue adaptation process after exercise to orchestrate tissue repair. So if you're exercising, you are promoting the pathway for the hormone biosynthesis, which then allows the increases in energy metabolism in a number of key places, which then allows a lot of extra activity to happen regarding protein synthesis and everything else.
So that's why sauna is pretty good.
Yeah, but also why sauna then promotes the immune activity as well. So via heat and exercise, both of those are promoters for interferon gamma activity.
So when you say that NAD pH is the currency, this is I'm trying to hang along as good as I could, but what's going on? Is there a homeostasis you're looking for?
Yes.
Not too much or not too little. And what's the catch with us that have these issues in CFS?
So the homeostasis is then controlled by cortisol.
Okay.
So if interferon gamma is driving that activity, if things go wrong, cortisol gets promoted to inhibit interferon gamma, which then allows all of that to reset. And so by virtue of that, what you can expect is that the various pools which are responsible for ultimately then promoting cortisol, if they become low, are going to get depleted over the day, which then means that what you can expect is that the cortisol levels will be elevated at night. So in the evening, you'll have more energy, but you'll have sleep issues most likely, but you'll have your most productive times in the evening. And then depending on what happens with the certain pools, you might find that you're low cortisol in the morning. So you're dead in the morning and you're more active at night, like a night owl.
Okay,
so what happens?
Yeah, of course.
Well, what happens with the cortisol? So the cortisol, there is a sensor, and what it senses for, what is checked for is the glycolytic flux. So the ability to maintain glycolysis. So that means if the glycogen stores are low or there's low glucose uptake, then you're going to end up with impaired glycolysis, which is then going to lead to an elevation of phosphatidylserine. I'm not sure if you can see my mouse circling. Excellent. Okay, so if phosphatidylserine becomes elevated, it then decreased rather. If phosphatidylserine is decreased, it then promotes the increase of corticotropin releasing hormone, which then promotes adrenocorticotropic hormone. And that ACTH basically then drives this whole pathway up. But in addition to the glycolysis being inhibited, if you look at the enzymes, and I'll just show you that, look, I might show you it on the figure 1 because it's a little bit more obvious here. If you have a look at the glucose metabolism, so what we're talking about here is the sensor here is phosphatidylserine, so that's here, PS. So if there's anything that goes wrong anywhere in this pathway and we end up with low 3PG, so 3-phosphoglycerate, then this whole pathway is going to become inhibited, so therefore the rest of that stops, so we end up with cortisol being promoted. If, on the other hand, we have low NAD, then that dehydrogenase becomes inhibited, so again, we end up with low phosphatidylserine. If we have an issue with P5P levels, then that transamination is going to be inhibited. If we've got problems with the amino acids there, so if we've got alpha-ketoglutarate and glutarate, homeostasis issues for various other reasons, then again, we're going to end up with low phosphatidylserine. Now, when we're looking at the P5P, so that's the active form of vitamin B6. Normally, you'll see people get elevations of B6 in the serum, but conversely, when you see the elevation of B6 in the serum, it happens to actually be low inside the cells when you look at the right tests. When you look at the P5P or B6 metabolism, what you find is, again, interferon gamma has a feedback loop or a sensor through the B6 metabolism, and it uses that to sense tissue damage via transforming growth factor beta 1 levels. So if there's tissue damage, if the signaling for that tissue is elevated, so transforming growth factor beta 1, it inhibits an enzyme called PMPO, which then inhibits the conversion of the different forms of B6 and also the degradation of pyridoxal to pyridoxate. So this can lead to elevations of serum B6. This is on top of any other issues with, for example, low zinc and low magnesium, which then inhibit the pyridoxal kinase, so PK, as you see there, and conversion from pyridoxal into P5P. Or indeed the issues with the riboflavin metabolism, some of that which we were talking about before with the glutathione peroxidase and reductase. So what happens there is if P5P then becomes low, we then end up with a promotion of cortisol. We also end up with low P5P, so that's going to affect neurotransmitters. So it's going to affect your dopamine synthesis. That's going to affect your ability to convert glutamate into GABA via GAD, glutamate decarboxylase. And it's going to create issues with your serotonin synthesis, from 5-HTP. There's another P5P there. So you will notice the effects. You'll have low dopamine, you'll have low neurotransmitters, but you'll also have high cortisol. And you could imagine that scenario could be described as anxiety and tachycardia.
Yeah,
but
and bad memory. Maybe.
Yeah. Yeah. I mean, you certainly see brain fog and things like that with
exactly.
the low neurotransmitters.
Yeah.
But what happens here, in addition, okay, so that cortisol release was one thing that we just talked about, but then you've also got inside, you've got the metabolism between the active form, so that's cortisol, and the inactive form, that's cortisol. And then you've got these HSD enzymes. So you've got 11 beta 1 and 11 beta 2. So when NADPH is elevated, so that's what we were talking about before with the interferon gamma activity and then exertion or heat or whatever you want to look at there, but exertion largely, then it's going to be driving.
Can I just ask you, if you are continually in the interferon gamma environment and the NADPH is elevated, would that ever be depleted, the NAD, or would it just continue to find sources to make it?
Well, so the NAD, okay, the NAD biosynthesis is the kynurenine pathway. So that's where it takes tryptophan, which is the other, like the precursor towards serotonin, and then drives that down the pathway towards NAD. I'll show you that in a moment. Actually, in fact, I might even show you that now, and we'll come back to here because that's actually relevant to these two enzymes and how that also acts as a sensor. So if we were to look at here, so we've got tryptophan. We can see just at the top here in the middle. So tryptophan goes down through here, goes down, and you see that's activated. So IDO1 and TDO, that would be, you'd see Ron Davis's work talking about the IDO1 trap. It appears to be that's the interferon gamma activity or the transformations. So if cortisol is elevated, interferon gamma is elevated, tumor necrosis factor alpha is elevated, then IDO1 and TDO gets promoted. So then the bias of tryptophan's conversion ultimately through to NAD becomes promoted relative to its potential conversion to serotonin if it goes the other way. So that NAD biosynthesis pathway, though, the thing is that gets inhibited by various other things too. So if we've got problems with P5P, if we've got oxidative stress, if we've got low iron, if we've got various things that will inhibit that pathway, it'll end up inhibiting the levels of NAD. So then once the NAD pool becomes decreased sufficiently, what we then end up with is something to reset that and allow things to go back to normal. So there has to be this regulation. So if we were to look at here, the cortisol to cortisone, what we see is that the primary sex hormone, so that would be testosterone in males and estradiol in females, it inhibits the activity of this HSD 11 beta 1. So that's the conversion of the cortisone into cortisol. So if the primary sex hormone happens to be lower, then this activity, when NADPH is elevated, is allowed to continue, which then elevates the levels of cortisol. However, going the other direction is the HSD11 beta 2. So similarly, and I've only found literature showing females, and that was rats. I'm assuming that we'll find the same thing with males, but the same thing happens here. So the the HSD11 beta 2, that requires NAD. If the levels of NAD are low, then the cortisol levels are going to increase. So the combination of the elevation of the cortisol levels here and then the cortisol release, which is via the phosphatidylserine, ends up leading to the inhibition of the interferon gamma, which then resets the whole pathway and allows the pools to reset and to refill.
Because you said in the protocol that people who the body do not want to have the interferon gamma response, because then you have all these crash symptoms, and that's why people are like addicted to fear and stress, because it creates cortisol.
That's right. It gives them an inkling of an energy envelope by inhibiting the interferon gamma activity. Once you understand that the bulk, apart from the dysbiosis symptoms, which is creating the acetaldehyde and the histamine levels and all the other stuff that we see there, the other side of that is the bulk of the other symptoms are coming from the interferon gamma activity, so the immune response, and more the point that that's unsupported. So somebody who has normal levels of minerals, somebody has the ability to metabolize these reactive oxygen species, for them, interferon gamma actually leads to positive, like benefits. But when it becomes unbalanced, it dysregulates, this whole pathway. And then you could end up just stuck in this cycle where you never actually clear the pathogens, and you won't anyway because of this other biofilm issue. But you basically just drown in oxidative stress every time that you exert yourself, or every time that the immune system steps up and tries to do something useful. So cortisol then becomes your friend in many ways, at least as far as actually small, increases of quality of life. But ultimately, it doesn't benefit you as far as actually suppressing the reservoirs or the pathogens which are keeping you sick and keeping you stuck in this in the first place.
That's pretty crazy that cortisol becomes a crutch that you live by, kind of, because I can see that in myself, that I'm a political scientist, but I have been craving like news and like stress and fighting, and that made me feel good to a certain point, and then if I went over that point, I crashed also from that. So it seems like that also has its limits.
Correct. And look, there's other sides to that too. I mean, look, what we're talking about here are pathogens that are susceptible to the interferon gamma activity. But what I haven't talked about yet is the interferon alpha activity, which is also needs to be in the model. The two directly both support each other as kind of like a flip-flop. So when there's interferon alpha activity, it kind of primes the pump, as it were, sets it up so that interferon gamma can actually exert its influence. And that does that in one case by another enzyme that's not shown here called xanthine dehydrogenase, but it basically generates some of the metabolites that's needed for xanthine oxidase. But anyway, the interferon alpha activity, you've probably seen Rob Fair's itaconate shunt work.
No.
So the hypothesis. Well, Rob Fair's his latest work has been really mapping out itaconate, which is the type 1 interferon. So interferon alpha ultimately produces a metabolite called itaconate. The itaconate ends up inhibiting certain things in citric acid cycle. So namely, it'll be inhibiting succinate dehydrogenase. And this has a benefit towards reducing energy availability for infected viral cells, but it also gets used to inhibit energy for microorganisms that have an enzyme called isocitrate lyase. So if you've got candida, for example, that's probably a good one. I can show you that on one of the other diagrams. If you have candida, what it does is it basically inhibits the available energy metabolism for that pathogen. Here we go. So here on the diagram, hopefully you can see my mouse, ICL, so isocitrate lyase. What happens is that it takes D-isocitrate and it produces glyoxylate. That's part of the reason that some people have issues with oxalates, but it's not the only one. I'll come back to that. Then returning succinate. So if interferon alpha is promoted and then it produces itaconate, and then itaconate comes over here and inhibits succinate dehydrogenase, what that means is that the levels of succinate become elevated, and then that impairs the enzymatic activity of isocitrate lyase. So the elevation of succinate effectively inhibits the energy metabolism of the microorganism. So there is a benefit then to the host via that mechanism. In fact, of the two, the itaconate activity and the interferon alpha activity is the least impactful on the energy metabolism. So it's actually it's unpleasant. Like you've got reduced energy, you've got certain symptoms, but it's less of an impact than interferon gamma activity. Interferon gamma activity is the the most unpleasant when it's unsupported. So yeah, so the interferon alpha activity and the itaconate production um, ends up inhibiting certain energy metabolism, but it also, hang on, is it further down here? It also inhibits part of, and is this shown here? It should be here somewhere. I apologize.
No, it's
it may not be. Oh no, I did. Okay. It inhibits M-mut or MMCM, which then inhibits one of the catabolic pathways through to succinyl CoA. So some of the energy that might be available from BCAA catabolism and from odd-chain fatty acids, some of the BCAAs will end up here being like that pathway being inhibited. It won't be able to make use of that to feed the citric acid cycle when interferon alpha is elevated. Ultimately, though, it does benefit the host by helping to inhibit the pathogen. Anyway,
okay. Yeah.
Now what happens is really interesting. So if you understand then that if you have pathogens or antigens which trigger an interferon alpha response, and by virtue of that are inhibiting the interferon gamma response, it's possible to then allow for the proliferation or microbial bloom of certain microbial pathogens when the immune system is busy attempting to deal with viral antigens, or in these other cases, these isocitrate lyase expressing microorganisms. So if you have a viral infection or you are injected with antigens or something that produces antigens or viral antigens, you might have a period of time there where the immune response that's suppressing the growth of these other microorganisms is inhibited, which then allows for when the body has actually finished dealing with the viral antigens, it then means that you come back to post-viral fatigue and the rest of the the unpleasantness that goes along with this, and potentially CFS. So you now have this upregulated interferon gamma response cleaning up the mess that was created while the immune system was busy dealing with the other class of pathogen.
So that's why people, like, after a kind of different kind of
COVID or
infections by
yeah,
viruses develop.
yeah, develop that rebound on the other side. But it also explains why somebody who already has CFS, more often than not, when they get COVID or they get some other viral infection or a cold or something, they actually quite often feel better while the immune system is dealing with that class of pathogen and not the microbes, and not producing the interferon gamma response. But then, of course, they have a boomerang or rebound on the other side, once things settle down with the viral antigens. This is where it gets really interesting for COVID and for also for the vaccine injuries, is because of the SARS-CoV-2 spike protein. So one of the things that's known to do is actually create certain clotting issues. So you can end up with these thrombosis, or you can end up with rouleau from various other mechanisms that can be, things like the zeta potential, that's the electrical charge on the outside of the red blood cells. That can be reduced, which then causes the red blood cells to clump together. That can then lead to hypoxia. They can also have other issues with oxidative stress and similar issues. Inflammatory proteins also creating the same thing. But ultimately, once you've got this hypoxia, that hypoxia then can lead to that reactivation of these herpes viruses via that protein that we're talking about before, that HIF protein, hypoxia-inducible factors, which then means that if you've had, for example, a recent COVID shot or a recent infection, you keep running the risk of reactivation of Epstein-Barr or varicella. You might have shingles. You've probably seen quite a number of reports of people with shingles now in the last few years.
Exactly. Yeah.
And yeah, so that reactivation is basically mediated by the stabilization of that protein and then any of the upstream factors. or a combination of the upstream factors. So like if you have hypoxia, but you've also got the low iron that's expected after you've had that chronic infection for a while, or the low zinc or the low silicon, then yeah, you are more predisposed towards the viral infection potentially leading to the reactivation of the slumbering beasts. So your Epstein-Barr virus or your, varicella or whichever latent infections
Mm.
that you may have.
Or you're maybe susceptible for something to come into your system while you're going through a COVID or spike protein in your system, that you get some random herpes virus or whatever in that
That's
period,
exactly
maybe.
right.
Yeah.
Yeah, so basically that's the thing. So if you lead to a point where the system cannot metabolize the reactive oxygen species and it runs low on vitamin C, that's one influence to not allow the prolyl hydroxylases to work. If we've got hypoxia, that's another major influence. But as you can see here, low silicon, low iron, low zinc, or any factors, and that could just be low magnesium, or it could be, impaired substrates for like glycolysis or fatty acid oxidation. However, we end up with low flux through the first half of the citric acid cycle and then low alpha ketoglutarate, or we could have other issues with transaminations, basically leading to reduction of alpha ketoglutarate. Then, yeah, however, we end up with inhibition of the prolyl hydroxylase. Oh, and sorry, of course, elevation of succinate is another one. So the atacanate pathway, by inhibiting the succinate dehydrogenase, potentially also can then lead to the inhibition of the prolyl hydroxylases as well. Hypothetically, I could see how that would potentially allow for the body to find and to clear out the latent infections by triggering them to reactivate. The problem is that if the immune system is not capable of, clearing out the infected cells faster than the infected cells can then infect other cells, then it appears to be something that's going to drive us backwards in the long term. So ideally, I think the factors that lead to the chronic reactivation are not not helpful, or accelerate the slippery slope towards severe / cancer / everything else.
Yeah, and we spoke about EGCG
Hmm.
previously. I read that EGCG and the vitamin C upregulate P53. That is the
Hmm.
cancer
Tumor
search and
suppressor gene.
destroy. Yeah,
That's
and
right. Whereas there's studies
spike
showing the spike
protein
protein
downregulated.
inhibits that.
Yeah.
Yeah, that's right. And BRCA1 as well. It's really interesting. Like you look at the spike protein and you look at the various different features of that spike protein, and it's just astonishing that you would have, some sort of wild type spike which has all of these features that happen to do all of these things. It's quite incredible that such a thing would be found in nature and not in a lab.
I think it's a bioweapon, 100%. I think this is yeah.
I
This
think
is
that's the only way
I
you
think
look
they
at it.
found like a furin cleavage site was totally manipulated. So, but that is
Yeah.
another discussion. But I think
Hmm.
for people, most of us that's gone through either the virus or vaccination. I didn't want to have a vaccine because
Mm.
I didn't trust it. But what
Hmm.
would you suggest people to? Are there anything you can do, like in terms of supplement to
To clear
upregulate
out.
P53 and reduce the clotting that you?
Well, the clotting, look, there's a number of ways to deal with the clotting. The problem is that if you have, in fact, even the body's got a route towards actually degrading the spike protein. The problem
Okay.
is that if we've got persistence, so if there is somehow some reservoir of SARS-CoV-2 somewhere, and that could be in the brain, there's hypothesis that it could be in the microbiome, which is wild if that's true. There's other studies are suggesting that the virus even acts like a bacteriophage, which again, if wild if it's true. But somewhere, if there is a reservoir of the virus, or if you've had one of the mRNA shots, which happen to, as we now know from multiple studies, there are issues which cause the cells which are transfected to continue producing spike protein for an indefinite time. So
Okay.
in one of the studies, I think the limitation was 187 days, I think it was. If you are still continuing to produce that spike protein, then you have a load, which is then potentially adding to this clotting issue. So you can break it down. There are different things. Nattokinase is something that's known to help degrade the spike. The body itself will use a number of different routes to get rid of it, but there's neutrophil elastase. So one of the immune cells, it produces an enzyme which is then able to degrade or unfold that protein. The problem is is that when it unfolds the protein, it creates an amyloid-like protein, which then creates a new clotting issue. It creates this sticky white protein, which I think has been showing up in certain samples. So
Okay,
it's
but natto could be,
nattokinase appears to be quite helpful for that.
and yeah, that's good.
But I think as somebody who's dealing with, a long hauler, so long COVID or vax injury,
Yeah.
sort of 2, 3, 4 years, down the track, nearly, I don't think that unless they've had recent shots or something, there should be no real reservoir that's still producing that. There are tests that can be done. There are in fact, there are even tests that can show you which spike, which brand of jab that you had, because there were very subtle differences in the sequencing between the Moderna and the Pfizer that you can actually detect which was used to transfect the cells just by a PCR.
Interesting. Okay, but going back to the protocol, do you feel like you have covered, given a general look at some of the mechanisms now, or
some of the mechanisms? Look,
yeah.
Given a sufficient amount of time, we could cover this in depth for probably, I don't know, maybe 4 hours or more, and still probably leave some things behind.
Yeah.
Look, there are other interesting things to be aware of. One of the ones I'll maybe just highlight here, apart from the dysbiosis and certain p-cresol and things, which inhibits the catecholamine, so dopamine through to norepinephrine. One of the things that's really interesting is this mechanism that I talked about before, where the acetaldehyde essentially can deplete the NAD, or the mineral deficiencies can end up inhibiting the aldehyde dehydrogenase activity. But ultimately, if there is an elevation of this aldehyde metabolite of dopamine, so dopal, and dopamine at the same time, there is actually a pathway in the body towards morphine. So there's an endogenous morphine biosynthesis pathway which is upregulated. So essentially the body is creating an opioid.
Whoa.
So why that gets really interesting is that a number of some of the other symptoms that you can see in CFS do actually look like chronic morphine use or chronic opioid use.
But for me, that takes naltrexone that binds
Well,
opiates.
that's exactly why low-dose naltrexone becomes very interesting in that context. Similarly, just going back to what we were talking about before with the
we are both alcoholics and opioid users at the same time.
Users.
Jesus.
Yep. And it's measurable. This is the funniest part, is that it is measurable. You can see it sometimes in the urine tests. One of the other ones that's interesting too, there was another popular narcotic called gamma hydroxybutyrate, which is, I think, also used as a floor cleaner. But gamma hydroxybutyrate, you see it in the organic acids tests. I think it's marker maybe number 74 for hydroxybutyrate. And what happens there is that the GABA metabolism, so GABA can re-enter the citric acid cycle via the GABA shunt, SSAL, so it's another aldehyde metabolite, and it goes through ALDH 5A1, which requires NAD. If NAD is low, so it's inhibited by acetaldehyde, and then ultimately we have an elevation of SSAL at the same time as we have this interferon gamma activity, and we have the elevation of NADPH, then what we see in the organic acid test data is an elevation of gamma hydroxybutyrate. So the body is making 2 narcotics under these circumstances.
Why is it to like remove pain, do you think?
I think there's a benefit from pain relief, but also the other thing with the opioids is that they drive up a pathway called CAMP and to protein kinase A. And that has the effect of driving glycolysis, and it also has an effect of driving up a number of pathways.
So it's actually like an emergency energy production route.
That's right. But the problem is if it becomes chronic, then you're going to end up with the downregulation of the CAMP-PKA pathway. So something I've been, just by the by, I've been poking around recently trying to understand why in some people they still had sluggish glycolysis even after all of the quantified variables had actually been resolved. So like we had problems that were causing elevated fatty acids because they weren't being oxidized, resolved those issues. We had other issues with the problems with the glucose transporters because of things like there was low chromium or low vanadium, or there were elevated cholesterols, which is another thing from low NAD. I'll come back to that. There were various different things that were visible in the data, and then even after resolving that, in some people, they still had issues with glycolysis. And what was really interesting is that there was, if you were to promote CAMP-PKA, the glycolysis would actually then be working again, which was then suggesting that it had been, the homeostasis had actually been upset previously, perhaps by the endogenous opioid synthesis. In some cases, there were people where they'd been given opioids for long periods of time as well. So it was not unexpected in those cases. But it's very, very interesting. It's just yet another way that the unexpected ways that we can see that the metabolism ends up being inhibited.
So if you tie this to the stages of the protocol,
Hmm.
could you do like a quick just recap of the stages of the
Sure.
protocol in terms of what we have been witnessing?
Yeah, yeah, absolutely. So, I mean, look, stage one of the protocol, maybe I'll just jump off here and I'll see, I'll come back to me here. I'm gonna maybe bring up the current version somewhere of the protocol document. Just one moment. There are some nice updates coming at the moment. What's there is working well, but we are always looking to improve.
Yep.
So there are some exciting things on the way, improvements for intracellular bacteria, so spirochetes and people from Lyme disease. We've also got things for people with strep infections. There's some improvements coming there. There's a number of really, really interesting improvements. So basically, where things are looking to go at the moment is trying to do away with what we're using the antiseptic for, which is in the mucosal interfaces, and then replace that with probiotics,
Hmm.
which perform the same function. And then, of course, the best part about that is they continue to perform the same function after they've
Hmm.
colonized, as opposed
Exactly.
to requiring a daily dose. And of course, that's their job. Just going to bring this down. Okay.
So,
So in the
what
protocol,
you're kind of saying is it's the same mechanism. It's a virus and pathogens like Candida, etc. But people
mm,
are different and have different kind of pathogens and viruses that
correct.
have a different result in their body. So you have to tailor the protocol to them. So when people go
Well,
online and say it didn't work for me, you can ask them, do did you do the testing? Did you
correct. It's one of the
exactly.
challenges. People look. It's a gargantuan protocol. There are pages of supplements that need to be taken. There are ways to, ultimately, where I'm hoping this goes fairly soon is that we'll have a few vendors stepping in where they'll have all of these available as like a lozenge and some powder and some
Hmm.
probiotics, and then basically it'd be very convenient and easy to use. Unfortunately, early adopters, we kind of have to deal with the clunkiness of it.
Yeah, and people who
So,
are, my point was that people who are
mm,
want a quick fix,
mm.
this is not a quick fix. This is a really meticulously
Well, it's
science-backed and
yeah, it
individualized
does
protocol.
both. So what we do in stage one is, look, there is a certain amount of bumpiness that is currently unavoidable for certain reasons. And maybe I'll just take a step back here in the document and I'll just go back to there's a little image here which kind of tries to spell it out.
Yes,
So one of
that's a
the
good point.
one of the things with this is this, because we know that the immune activity is driving the symptoms,
Mm,
anything that we do to improve the efficiency or the activation of that immune response is going to make somebody feel worse.
mm,
So somebody who has been chronically ill for a while, let's say that they've got, severe malnutrition, which is essentially being induced by this inflammatory cascade, and they've got hugely impaired energy metabolism. So it's not just the muscles and the brain and the other organs which are feeling the result of that impaired energy metabolism, it's also the immune cells.
mm.
So when you start restoring glycolysis, when you start getting that energy metabolism working, it's a high priority task for the immune response to start clearing out any of these foreign proteins.
Mm.
So if you start restoring, let's say zinc, for example, which is used dramatically throughout the different parts of the energy metabolism, or magnesium, and suddenly the immune activity ramps up, you feel like you've gone backwards. You're going to feel sick. You're going to feel,
Mm,
like you've taken a big step backwards. And then
mm.
a couple of days later, you'll find that the baseline has increased. So basically, the immune system starts, picking fights with the visible targets.
That's what
And
happened to
so,
me throughout. Like, I taken supplements
mm,
and I have felt like shit, and I was like, "Fuck
mhm,
this supplement." So that's what's
yeah,
probably happened.
that's exactly what it is. Everyone bounces off the wall. They take something and they go, "Oh, I took carnitine and I feel worse."
Yeah.
It's like, that's it. I can't take that. I must be something, something with my metabolism. I can't take carnitine.
Mm,
And the reality is that everyone you go through, if you look at the list of the supplements in the protocol, people should freak out probably about half of the things that are there. They should make them, all sorts of nervous because, oh, I've taken that and I've taken that and that made me feel horrible. I don't want to take it again.
mm,
Well, the reality is that the immune activity is going to make you feel horrible. And not only the immune activity, let's say that you've got candida. Let's say that you've got a number of these microorganisms that are producing acetaldehyde.
mm,
If you do anything which degrades the cell wall for that microorganism, then the contents of that cell are spilled out and then either somehow metabolized by, maybe some other helpful species around it, if there's, lactobacillus and bifidobacteria there to do something useful. But otherwise, those toxins end up circulating, and the host
mm.
metabolism has to actually metabolize that into something else. So you might end up with a big wave of acetaldehyde in the process of killing off a patch of candida.
Exactly.
So if you go into this and it's like, imagine the trap. Every time you take something that's good for you, you feel worse.
Mm.
The natural instinct is to stop taking things, and then
Ex-
you
Just
end
like,
up, yeah, you'll sit in a dark room eating cardboard because you can't stomach anything, and then it's just, yeah, it's only going to go one way. So you have to make peace with the idea of weathering some die-off. And we do various different things in the protocol to smooth that out. The next update with some of the other probiotics which are being included further smoothens out that initial period with the die-off and some of the other things. But the Herxheimer effect is real. If you take antibiotics, for example, everyone's got the story, oh, I took amoxiclav and whatever, and I felt horrible for a couple of days, and then I felt, pretty good after that. And then it all snowballed again a month later. What happens is that you do get that Herxheimer effect. You do get that die-off. When it's not immune activity, it's circulating toxins and the metabolism of
ah,
them. So you can't go into this thinking that it's going to be a nice journey all the time. But, the other side of this is that we do a number of things to support the energy metabolism, to support the detox pathways. So, for example, we're talking about acetaldehyde being one of the more unpleasant toxins in this. So we have included in the protocol, where is it? There is a thing called dihydromycetin, which promotes the aldehyde dehydrogenase activity. So that's the ALDH that we were referring to on the diagrams before.
mm,
However, it of course needs NAD, so we've got something else in there. You'll see there's B3, NMN, so it's a precursor towards NAD. That's already being included. There's going to be the various minerals that are required for that enzyme to work, so molybdenum and zinc and magnesium, so they're also included. All of these different things. I see lymphatic massage there, and we should probably talk about that. There's sleep, all of these different things that are required to ultimately start clearing out, the reservoirs of these problems which are keeping people sick.
mm,
So they're in there. If we were to look at the energy metabolism, and I used carnitine as an example before, if we understand that carnitine is required for transporting fatty acids into the mitochondria to get them oxidized, or the longer chain ones, if carnitine biosynthesis is inhibited for whatever reason, then you've got less energy availability from fat.
mm,
So knowing that that is a particularly problematic pathway, will include acetyl-L-carnitine in the protocol to act as I suppose as a workaround for that pathway not working at certain times.
mm,
So you're able to weather a number of these unpleasant situations just by keeping those pathways working. The challenge is going to be, though, is that because for most people, the primary issues are going to be in the gut microbiome, there will be other tissues, like the nasopharyngeal microbiome, sinuses, vaginal, lungs, wherever the dysbiosis and the biofilms are.
mm,
Whenever the immune system ramps up in those areas, if it's the gut in particular, you're going to have GI upset. You're going to have potentially, if the immune surveillance decides that it's a great idea to try to eject these pathogens, you're
mm.
going to get vomiting, you're going to get diarrhea, and that's just a normal part of the way that the body tries to deal with these infections. So understanding that, you can see in this example, you'll see that there are periods of GI upset expected, particularly in the beginning where we first get the immune response working. and then that settles down. The low-hanging fruit's been picked. The energy envelope starts coming up. You start feeling pretty good, and then we get into stage two. Stage two, we start, chipping away at the biofilms and doing things to actually work on that microbiome. In fact, towards the end of stage one, where we start putting in the probiotics, we're already starting to do that. So the expectation is we're going to get into stage two, and we're going to have, certain GI upset during that time. And then that settles down, the energy envelope's up, we're actually feeling pretty good. A lot of people along the way, if they do enough work in stage two, they're not going to have such a difficult period in stage three.
Okay.
Stage three, where we really break open the biofilms and ramp up that immune activity, intentionally promote it. If everything's gone well at that point, that might actually be a very mild blip in stage three, and they might just suddenly find they've got all this extra energy. So it really just depends. Like, everyone's going to have a slightly different, journey around that. But if stage two's gone very well, then stage three, there's less work to be done.
Could this protocol be combined with naltrexone?
Yes, absolutely. The
Okay.
low-dose naltrexone is compatible with the protocol. Can't give medical advice, but I can tell you there's compatibility of.
Yeah.
Yeah,
But
it is
none of
compatible.
this, like if you do this in a controlled environment with the resources available and the people available, there is is not. Can it be dangerous? And how do
So
you have any
the
words
things
on
that
this?
I would draw attention to would be if you have a period where you are really chipping away at gut microbiome issues and you're inducing diarrhea, and that's been going on for a few days, then there's a possibility that you're going to be having difficulties with hydration and electrolytes.
Yeah.
Now, bearing in mind that the protocol itself, the protocol itself is going to be supporting those electrolytes very, very well.
Yeah.
There's actually a page on electrolytes. I'll go past the rationale of all the different inclusions and testing and blah, blah, blah. Hang on a minute. But there is a page there on electrolytes, and we actually go out of our way to make sure that the intake of those electrolytes is aimed to refill deficiencies. So you'll see that, for example, sodium, we have at least 2.5 grams of sodium a day. And some people will take anywhere up to even 10 grams a day in severe states. There's a particular pathway that when that interferon gamma activity is elevated, then it triggers dopamine to be elevated in the kidneys, which then triggers the kidneys to excrete sodium at a high rate. And so by virtue of that, you become low sodium. If you become low sodium, then you're going to get hypovolemia, you're going to feel horrible, you're going to have problems with neurotransmitters. You're going to feel like you've got quite a nasty flu on top of everything else, and woozy and nauseous and everything else. So increasing the sodium during that time is actually quite beneficial. Normally people then worry about, oh, well, what if I've got elevated blood pressure? Well, the elevated blood pressure is the other one. So that's potassium. So sodium is the extracellular pair, or half of that pair. Potassium is the intracellular partner of the sodium. So if you have low levels of potassium, then you end up with higher levels of sodium in the extracellular fluid in the blood, which then leads to the increased blood volume and the higher blood pressure. So making sure that there's not a potassium deficiency is the solution in most cases to preventing high blood pressure under those situations.
Okay, could you take sea salt with minerals in it instead of table salt?
Yeah, absolutely. I mean, if you want to use Himalayan salt or any of the other, sort of nicer salts, then by all means. You just get more trace elements and things which come with that. And that's another interesting conversation, because that's really where most of our trace elements and minerals and things that have come out of the soil have actually ended up in the ocean. And conceptually, it's really interesting that we basically, the way that our food systems work, just to take a tangent for a minute, is that we have the plants that are pulling the minerals up out of the ground. We then have animals that are eating the plants, and then we eat both the plants and the animals. And then some really, really intelligent person decided that we should then take the waste products from consuming those plant products and animal products, and then we should flush them out into the ocean. So that means that progressively over time, as the studies have shown, the soil where we're growing our crops has become depleted of certain minerals, and to the point where the mineral content of vegetables has dropped by over 53% since the 1950s. So adding insult to injury for trying to maintain the mineral status during chronic inflammation and infection is the fact that the food supply is now additionally problematic, even if you're trying to do the right thing.
Yeah. Okay. Is it so the 3 stages, remineralization
Remineralization and support, and then microbiome remodeling, and then immune promotion, and biofilm breaking.
Okay.
So they're described like at the top of each stage. So again, there's generally a nice warning towards, hey, there might be a die-off effect as you're doing this, and there's generally some hints around how that can be managed. Stage 2, you'll see. Yeah, we talk about that. Okay, so stage 2 is expected to trigger additional gastrointestinal immune activity, which is likely to be observed as diarrhea, blah, blah, blah. So we talk about then ways that that can be managed. You'll see in the next update that there will be some additional probiotics, which might also help make that less problematic for some people, depending on the mix of different pathogens that they're dealing with. We also then start introducing ionic MAM, which is that fulvic acid source. And we start off at a very low dose if needed. Most people will be extremely sensitive to fulvic acid. I've heard one person describe it as giving every cell in their body an oxygen mask, and it can be quite a dramatic and unpleasant shift metabolically. And then stage 3 is where after confirming, so we do follow-up data, the follow-up testing for mineral status. We then look to try to clear out the reservoirs. So we throw in some additional biofilm breakers. There's already quite a number of biofilm breakers in stage 2. What we'll do is we use high doses of alpha lipoic acid and N-acetylcysteine, along with certain mushroom supplements and high doses of the fulvic acid, which is another, so we've got three additional biofilm breakers being added into stage 3. So the big challenge for that is the psychological trauma, which is going to be induced by an upregulation of all of that immune activity. So you've just done all of this work. You've gone through stage 1, you've gone through stage 2. You're feeling pretty good at this point, and then you know that you're going into stage 3, where you're intentionally going to be doing things that may make you feel absolutely horrible for a period.
Or make you feel a little bit worse, but decent enough. It can, like you said, it doesn't mean that you
variable.
have to. Yeah.
No. So don't be afraid of it, but just allow that expectation. So once you understand that things like POTS, so the postural orthostatic tachycardia syndrome, once you've got problems with glycolysis, once you've got problems with the electrolytes, then you're going to have like the internal muscle tremors. You're going to have the cardiac rhythm issues. You're going to have postural orthostatic tachycardia syndrome. So the glycolysis, one of the things that happens is when you aren't producing enough ATP, then it means that the little pumps on the cell membrane, the ATPases, which are required to maintain the gradients of the electrolytes between the intracellular state and as intracellular levels and the extracellular levels, if those pumps can't keep up, then you start ending up with small, tiny little muscle spasms, or like internal tremor, or the cardiac anomalies that you see. So a lot of the people with the like long haulers, long COVID, where they're talking about these various different cardiac anomalies, the go-to before you do anything else is to make sure that the levels of the electrolytes are being supported and that the various things that are required to get glycolysis working are supported. And you'll find, the reports I get back from people is that, oh, look at that. I no longer have, the tremor. I no longer have the cardiac issues. POTS is gone. All of these things are actually really just mechanistic to this cascade, and are really easy to remediate if you're using the right interventions.
But in stage 3, should exercise be walking, or should you take it a little bit easier, or should you exercise?
Well, so the thing with exercise, and again, I think important to consider exertion or physical activity and immune activity, consider them as the same load for oxidative stress. In fact, exercise is an amplifier for that immune activity.
Yeah.
So if you consider they both end up promoting the same thing, you then need to kind of, if you're ramping up the immune activity, you might be in bed anyway. So like the concept of doing exercise might be thrown out the window. But on the basis that you aren't, if you can still, walk and move around, then by all means, the same as if you were not having CFS and you've got the flu or something, play it cautiously. But again, a little bit of activity may be beneficial towards that immune response. Conversely, too much activity and you might be drowning in the oxidative stress and regret it.
Yeah.
But you can always, add in, and you'll see that mentioned in stage 3. So it talks about if the cortisol heart rate becomes elevated for long periods, so above 6 hours, or immune-related tissue pain inflammation extends beyond 3 days per localized tissue. So like if it's in wherever that infected tissue is, it might be in the gut or the sinuses or whatever, It says here, take a few days off the mushrooms, double the vitamin C, and decrease the spirulina, which was in there. Has that actually been altered to a smaller level? So that was increased in stage 2. And so what that does is just tries to calm thing down. You know, if somebody happened to have prescription for some sort of corticosteroid or something, and they felt that that was appropriate, so if you had someone who had COPD or asthma and they happened to already have an inhaler, they would probably already gravitate towards something like that if it was getting too, you know, too much.
Yeah, because when you said spirulina, this square here is something you added to the stage 2, so that's why it's mentioned in the previous.
That's right.
Yeah. Okay. I just have to digest this, and I would really love when we go forward and the protocol is updated that we can maybe have another talk. And but this, I'm going to upload this, and people are going to enjoy it, I think, very much. And I just have to thank you, Josh, for putting so many hours. And you are a engineer in systems and engineer, so this is a really interesting way to see how you work in another field and how advanced our body is. It's just a super miracle machine. And thank you for all your work, and I really look forward to following your work, and I just cheer you on. And
thank you very much, Nicholas. Yeah, really, yeah. Look, I appreciate your time today too.
No, thank you. And I think I'm going to upload this, and I think people are going to enjoy it. So have a really nice day, and talk to you.
You too. Thanks, Nicholas.
Cheers.
Bye.